Imagine if you could be a time traveler for your computer science exam. What if you could see your completed, fully graded paper before you even start and just work backwards from success? Well, welcome to this explainer. I'm your host, and today we are going directly into the mind of a Cambridge examiner. We're going to dive deep into the architecture of the internet, the rise of cryptocurrency, and exactly how we defend against sophisticated cyber threats. But we aren't just memorizing definitions today. We are building your exam strategy blueprint from the ground up. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's get into it.
Here is our game plan for today. We'll decode the internet versus the web, map out how DNS locates pages, unpack digital currency, and analyze top cyber threats and defenses. Finally, we'll wrap up with actionable exam strategies.
Section 1. The Internet versus the World Wide Web. Let's clear up a massive misconception right out of the gate.
Okay, look at this comparison, because getting this wrong is a classic trap that costs students so many marks every single year. The contrast here is absolutely foundational. The internet is the literal physical infrastructure of interconnected networks. Think of it as the roads, the highways, the massive underwater cables, and the TCP/IP protocols that dictate how data travels across all that hardware. It's the foundation. The World Wide Web, on the other hand, is just one service that sits on top of those roads. It's the collection of multimedia pages accessed via web browsers using HTTP or HTTPS protocols. Think of the web as the shops and buildings located along the internet highways. Email is another service on those roads, but it is not the web. So, when an exam asks you to describe the differences, do not just dump isolated facts. You need to explain that the web inherently relies on the internet's physical infrastructure to function, but they are not the same thing. Connecting the what to the how is exactly what transforms a simple, low-level factual statement into a top-tier comprehensive answer that examiners love to see.
Section 2. Locating pages and cookies. Now we know what the web is, but how do our devices actually find things out there? This right here is the Domain Name System, or DNS process. If you want maximum marks, you have to treat this like a strict recipe. Your DNS acts as a critical translator. Why? Because humans like words, but computers need numbers. When you type a text-based URL into your browser, your computer actually has no idea where that is. It's like having someone's name, but not their phone number. So it follows a highly systematic flow. First, the user types the URL. Second, the browser asks the DNS for the corresponding IP address. Third, the DNS searches its massive database to map that specific text URL to its numerical IP address, something like 107.162.140.19. Fourth, that IP address is returned and sent right back to your computer. And finally, step 5, this precise sequence allows your browser to connect to the correct web server and download the HTML files. If you skip a step in your exam, you drop a mark. Every single link in this chain is absolutely vital.
Once you actually connect to the server, the site might drop a cookie on your machine. Now, examiners love to ask you to compare session cookies and persistent cookies. Specificity is your best friend here. Session cookies are purely temporary. They act exactly like virtual shopping baskets. You put items in, but the absolute second you close your browser, that session ends and the cookie vanishes into thin air. It is stored in temporary memory. Persistent cookies, however, are a different beast. They stay stored locally on your hard drive to remember your user preferences, your login details, and track your habits over time. They don't vanish when you close the browser, they sit there until their set expiry date is reached or you manually delete them. Explaining exactly what temporary means versus data residing permanently on a drive is how you demonstrate true technical mastery to the person marking your paper.
Section 3. Digital currency and blockchain. Let's venture into the financial frontier of the web. Cryptocurrency. The crucial point you need to hammer home here is the concept of decentralization. Unlike standard digital currency, which relies entirely on centralized banks and governments to verify exactly who has what money, cryptocurrency operates completely without state control. It relies instead on advanced cryptography and a decentralized blockchain to track transparent transactions securely. There is no single central server holding all the data. That decentralization fundamentally shifts how trust and security are handled online, completely removing the traditional bottlenecks and vulnerabilities of a centralized banking system.
And here is the genius of how it actually works under the hood. Look at how blockchaining relies on unique hashes to maintain this insane level of security. Think of a hash as a digital fingerprint. Every time a transaction occurs, a new block is created. This block contains 3 things: the data itself, a unique hash value generated by a complex algorithm, and, this is the magic part, the previous block's hash value. This intricately, mathematically links them all together into a chain. If a hacker tries to illegally access or alter even a single piece of data in one block, its unique hash fingerprint changes instantly. And because the next block is looking for the old fingerprint, that change breaks the link to all following blocks. It creates a cascading failure that immediately alerts the entire network to the tampering. Understanding this specific mechanism, the avalanche effect caused by a changed hash, is the absolute key to proving you understand blockchain's inherent security.
Section 4. Top cybersecurity threats. Because let's face it, that level of security is absolutely necessary on a web fraught with dangers.
Malware comes in many destructive forms, and I'm telling you right now, examiners love testing the specific distinctions between them. I see students lose marks all the time because they just vaguely say malware breaks your computer. You need to be precise. For instance, a virus specifically needs a host file and requires human action to trigger, like you actively clicking a dodgy email attachment. A worm, however, is a completely standalone spreader. It does not need a host, and it can autonomously multiply and blast through weak networks all by itself. A Trojan disguises itself as legitimate software, like a fake game or a system update, to trick you into willingly installing it. Spyware silently gathers your keystrokes and data in the background, adware floods you with unwanted pop-ups, and ransomware has one very specific, ruthless goal. It encrypts your data, rendering it completely unreadable, just to extort money from you in exchange for the decryption key. Nailing these exact technical definitions is what separates the top grades from the rest.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by multiple grade boundaries, so join them right now. Subscribe, turn on notifications, and let's get back to it. Because malicious software isn't the only vulnerability out there. In fact, often the easiest way into a highly secure system is simply by manipulating the human operating it. How exactly do cybercriminals weaponize our own emotions?
The answer is social engineering. This is a topic that comes up again and again. Social engineering bypasses technical hacking entirely by exploiting our psychology. The human firewall is always the weakest link. Hackers might exploit our curiosity by leaving an infected memory stick in a company parking lot, just waiting for someone to plug it in to see what's on it. They leverage our empathy and trust through phishing scams, sending emails that meticulously pretend to be from familiar, trusted companies, asking you to verify your password. Or they use raw fear with scareware, locking your browser with a huge flashing warning, or making fake IT support calls telling you your computer is deeply infected and they need remote access immediately. If a student writes on an exam that social engineering uses complex code to break into a database, they score 0. They miss the point entirely. Social engineering requires no traditional technical hacking. The cybercriminal simply manipulates the person into willingly handing over the keys to the castle.
Section 5. Defending against cyber attacks. So, with all these technical and psychological threats everywhere, how do we build effective digital fortresses?
One foundational method is biometric authentication. This uses your unique physical or behavioral traits. However, exams frequently ask you to evaluate these methods, which means you must discuss how each one balances convenience against cost and reliability. Let's say the question asks you to compare fingerprint scanners versus retina scans for a high-security facility. Your first point should establish that both are unique biological identifiers. But while fingerprints are a highly developed and relatively cheap technology, they can be spoofed with synthetic prints, or they might just fail if the user's skin is damaged or dirty. Retina scans, conversely, map the unique blood vessel patterns in your eye. They have incredibly high accuracy and are virtually impossible to replicate. Therefore, you would conclude that despite the significantly higher installation cost and slower processing time, a retina scan is far superior for maximum physical security. That is how you build a complete, high-scoring argument.
Now let's look at network defense. This diagram shows an incredibly powerful tool, a proxy server. A proxy sits exactly between your computer and the wider web. It acts as an active intermediary, filtering traffic before it ever reaches its destination. Here is the flow. The user's browser sends a web request, but it doesn't go to the web server. It hits the proxy server first. The proxy evaluates it, and then the proxy itself forwards the request to the web. By doing this, it completely masks the user's IP address, keeping your internal network secret. Furthermore, it acts as a massive shield. If a direct cyber attack, like a distributed denial of service or DDoS occurs, the proxy absorbs the massive flood of malicious traffic, leaving your actual web server tucked safely behind it, perfectly secure and online. And what about when you are transferring highly sensitive data, like credit card numbers? That is where the Secure Sockets Layer, or SSL, steps in. This is another highly systematic process you need to memorize. When your browser connects to a secure site, it first requests the server to identify itself. The server responds by sending a copy of its digital certificate. Your browser then checks the certificate against trusted authorities to authenticate it. Only after this exact, successful handshake does the secure, encrypted, two-way data flow begin. You'll know it worked when you see that familiar green padlock in your browser's address bar. Now here is a golden rule for your exam. Remember that encryption does not prevent data from being intercepted by a hacker. It just scrambles it, making the intercepted data mathematically meaningless gibberish without the specific decryption key. Stating that encryption stops hackers stealing data is factually incorrect and will cost you marks. It stops them from understanding it. That is a vital distinction to make.
Section 6. Exam Success Strategies. All right, we've covered the core theory. Now let's pull all these concepts together and look at the actual strategy of sitting the paper. Let's see how you apply this to absolutely maximize your mark potential. I want to show you two hypothetical students. Let's call the first one Alex. Alex often rushes, ignores the command words in the question, and just dumps random computer science facts onto the page. When asked about why one-time passcodes or OTPs are used, Alex writes a low-level answer vaguely stating that a user types in a PIN and it makes the website more secure against hackers. That's it. It completely fails to answer the how. Then we have Sam. Sam reads the command words, works systematically, and builds a high-level response. Sam details the exact mechanism, noting that after a user enters their standard password, the bank server generates and sends an 8-digit PIN to a pre-registered mobile phone. Sam notes the strict, short time limit on that code and explicitly identifies that the mobile phone represents something the user possesses, while the original password is something the user knows, creating two distinct, robust authentication factors.
Look at the examiner's actual commentary on this type of question. They specifically praise the systematic approach. The examiner notes that simply stating a technology makes things secure is never enough to demonstrate your knowledge. You must demonstrate the precise how and the why of the technology. You make a point, you provide your technical evidence, you explain how it works in context, and you link it back to the question. Whether you're explaining DNS routing steps, the avalanche effects of blockchain hashes, or the precise handshake of SSL, systematically backing up your facts and linking them to the specific scenario is exactly what separates a basic, low-level understanding from the true exam mastery that gets you the top grade.
So, are you ready to secure your grade the same way you secure your data? You now have the blueprint to structure your knowledge methodically. But as proxy servers and SSL protocols evolve, so do the hackers leveraging sophisticated social engineering. In a world where the human mind remains the ultimate vulnerability, beyond any firewall or encryption key, what will be your next line of defense? If you want to ensure your exam strategy is bulletproof, here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Drop a comment below with your target grade for computer science and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with your study partner, because your Cambridge success starts right here. I'll see you in the next explainer.